Hello everyone, it is my pleasure to give a presentation here. The topic I share is energy-efficient cooperative offloading from multi-asset point MEC in Internet of Things networks. Next, I will talk about this paper from three aspects: scenario introduce, system model, and experimental result. The general communication links, communication modes, and so on can all affect the energy consumption. If a mobile device has a long distance from the asset point accompanied by poor communication channel, offloading of tasks will use further energy than processing them locally. However, some studies have shown that the use of cooperative offloading by relay mobile device can save communication energy. We set up a local mobile device adjacent to multiple mobile devices, one of which can act as an relay mobile device to help the local mobile device offload application tasks to the randomly surrounded asset points. Each one deployed an MEC server, which provides abundant of computing resources. In some cases, an application task is supported to be divided into several segments in different sizes, so we can select multiple adjacent relay mobile device for offloading. But there are other cases where the application task is indivisible or only supported to be divided into limited number of segments. So we can select a most energy efficient relay mobile device for cooperative offloading. Each segment of the task can be processed on the local mobile device, the relay mobile device, and the MEC server separately. We propose an efficient cooperative task offloading scheme from multiple asset point MEC under delay constraint in the Internet of Things network. By selecting an appropriate relay mobile device and the asset point, as well as the task segmentation for cooperative task offloading, the energy consumption of the whole task computing process is minimized. By solving the optimization problem, the selection of the relay mobile device and the asset point, as well as the task segmentation, were determined. The whole process of task computing and offloading in the model includes three phases. The first is the local processing phase. The local processing phase includes the self-computing of segment IU as a local mobile device, offloading one segment from mobile device to the asset point, offloading on segment LU to MI and LMI to SJ, from mobile device to the relay mobile device. The second is the relay mobile device cooperative offloading processing phase. The relay mobile device cooperative offloading process phase consists of two parts. One is the relay mobile device computing of the segment that is offloaded from the local device mobile device, and the other is a segment that is offloaded from relay mobile device to the MEC server. The third is the MEC server processing phase. The MEC server processing phase consists of computing the directly offloaded segment from the local mobile device and the indirectly offloaded segments from the relay mobile device. We denote the application task length as long L. Let LU greater than or equal to 0, LU to SK greater than or equal to 0, LU to MI greater than or equal to 0, and LMI to SJ greater than or equal to 0. Represent the length of the computing segment as a local mobile device. Offloading from local mobile device to the asset point, offloading from local mobile device to the relay mobile device, and offloading from relay mobile device to the asset point, respectively. In particular, the task segment performed on the relay mobile device is LU to MI, and the task segment is offloaded from MI to MEC server. So the local task segment's length that is offloaded from the local mobile device to the relay mobile device MI is LU to MI and LMI to SJ. The delay constant for the directly offloaded segment on the MEC server includes the offloading delay from the local mobile device and the computing delay at the MEC server. Then we have this formula. The delay constant for the indirectly offloaded segment includes the offloading delay from the local mobile device to the relay mobile device and then to the MEC server, as well as the computing delay at the MEC server. Then we get this formula. Let's expand this formula to get this formula. The process of energy consumption is mainly consists of the following parts: the local mobile device computing, a relay mobile device MI computing, the local mobile device offloading to the relay mobile device, the local mobile device offloading to the asset point, and the relay mobile device offloading to the asset point. Let E represent the total energy consumption generated in the whole process. So we have this formula. Let's write the energy minimization problem as this formula. According to the problem, we can get the minimum value of energy consumption based on the comparative offloading of relay mobile devices. So the value of I, J, and K to determine the selection of relay mobile device and the asset point, and determine each segment length of the application task. We define the supported maximum task length as the number of data bits supported most by a task under a given delay constraint. Then formulate the problem at this formula. Problem is linear that can be solved efficiently through standard convex optimization technicals when MI, SJ, and SK are confirmed by previous question. We propose two benchmark schemes for comparison with our cooperative offloading scheme. Through numerical experiments, Our benchmark schemes include local computing only. The local mobile device will finish all task computing. Direct offloading. The local mobile device offloads application tasks directly to the MEC server without the help of the relay mobile device. This picture shows the relationship of the supported maximum task length in average versus delay constant. As the delay constant increases, so does the maximum length of the corresponding computational task. The supported maximum task length of our proposed scheme is much longer than the other two schemes because the relay mobile device can help offloading more additional database of the task, especially for longer delay constant. Compared with the direct offloading scheme, the local computing only scheme supports less data with the same delay constant. While the length of the input task exceeds the maximum length, the task will not be completed within the delay constant, which means that the longer the supported maximum length by the proposed cooperative offloading scheme with a local mobile device, the greater the computing capacities it has. This picture shows the relationship between the task length and the average energy consumption under the delay constant is said to be 0.3 seconds. Experimental results show the average energy consumption increases when the application task lengths become longer. By selecting an optimal relay mobile device, the energy consumption of the proposed scheme significantly outperforms the other two benchmark schemes under different task lengths. When the input application task is smaller, it will not occupy too much computing resources of the device because tasks will be done at lower CPU frequency, and the performance of the local computing only scheme is similar with other selections. But the local computing only scheme consumes more energy as the input task length of the application increases due to the increase of CPU exhaustion frequency. Our proposed scheme consumes relatively much less energy because part of the task can be offloaded to the relay mobile device and MEC servers for execution. This picture shows the relationship between the average minimum energy and the delay constant when the application task is L equal to 0.02 Mbits. The experimental results show that the energy consumption decreases with the increase of time constants, which means that the shorter time of the delay constant, the greater energy consumed by the computation task. Compared with the benchmark schemes, our proposed scheme has the smallest energy consumption at each delay constant setting, while the local computing only scheme has the largest energy consumption for all tasks are placed on the local mobile device. However, with the increase of delay constraint, the energy consumption of the three schemes gradually tend to some scale. When the delay constraint t equal to 0.45 seconds, the energy consumption of the benchmark schemes gradually become the same because the time constraint becomes loose, especially when t equal to 0.7 seconds. The energy consumption of the three schemes differs little, which suggests that our proposed scheme is quite suitable as a condition of strict delay constraint. Thank you for watching.